Today we study C17. You can download this PDF file for the lecture notes from recently we opened the website kpop.org, and in here every lecture file is in real time updated, and you can download it. For example, this is 17 Escape from Scientific Absurdity. Here, Escape from Scientific Absurdity, Series A, Series B, and then Series C we are working on. In here, we have C17. If you click, you can download this PDF file as it is. And you can click here to watch video. 플러스 C도 같은 면적이 되고. So this is in Korean, and now I'm recording the English version in here. This lecture is based on our previous K-pop paper. If you click information, and there's a link for the subscription and kpop.org, and we have written many papers regarding physics education. Let's see. All right. Okay. Three-body inertia tensor, published in European Journal of Physics. Let us click this. Now it has been read more than 4,000 times, and if you click this, you can download this paper. Okay, it is a very interesting paper. If you're interested in, please read it through. Very, very interesting. All right. Okay. Let's begin with cross product and Heron's formula. The paper we just download is this paper. We first consider what the cross product is. That we have two vectors A and B. If I translate any one of them or both of them to have their tails overlapped at a single point, then any two vectors construct a single plane that is two-dimensional. Sure, if they are either parallel or anti-parallel, it is just a one-dimensional straight line. But if it is not the case, in most general case, they construct a plane. The cross product is normal to that plane spanned by the two vectors, and there are two directions. We choose the direction of A cross B that is normal to this plane, but we can see there are two angles made of these two vectors. We choose the smaller angle between the two vectors, and we would like to rotate a vector that is in front. So rotate counterclockwise to let them overlap along a straight line. Put your right hand, swipe your fingers from A to B. Then the direction of your thumb of your right hand is the direction of A cross B. If I swipe from B to A with the right hand, then the thumb will be parallel to this direction. That is opposite. So this direction is chosen to be the direction of B cross A. So A cross B, B cross A, they are opposite. In addition, the magnitude of the cross product of two vectors is defined by the product of magnitudes, and n hat is the unit vector along either this or that. If it is if A and B are like this situation, the n hat is no vector on the plane directed as it is. And sine theta, that theta, this is the theta, the angle between the two, and actually this is smaller. We have 2 pi minus theta, the other larger angle. You can draw a parallelogram spanned by a vector and b vector. We have angle theta, right angle. The magnitude of a vector is the base of this parallelogram, and this is the height of this parallelogram. That is b sine theta, where b is the magnitude of the b vector and theta is the angle between A and B. Therefore, the magnitude of the cross product is the area of the triangle spanned by the two vectors. We consider the anti-commuting nature of the cross product. According to the definition, A cross B and B cross A cross, if n hat is the unit vector parallel to A cross B, then B cross A has the same magnitude as A cross B, but the direction is opposite. So minus n hat is the unit vector along the direction of B cross A. Therefore, the sum of the two vectors must be 0, and their values are exactly the same in magnitude, but direction is opposite. That is represented by the negative sign. We make use of the definition of the cross product to construct a multiplication table for the unit Cartesian basis vectors. We can draw a cube, and each side, adjacent 3 sides, we choose E1 hat and E2 hat. If E1 and E2 are given in like that, then E3 is defined by the cross product of E1 and E2. The order should be considered carefully because E2 cross E1 should be minus E1 cross E2. They are opposite. So E1 cross E2 is defined by E3. Okay, the normal vector of the plane on which E1 and E2 are placed. But there are two directions. This direction is E3 hat, and the other direction is minus E3 hat. And this is E2 cross E1, and this is E1 cross E2. Okay. So 1 cross 2 equals 3, 2 cross 3 equals 1, 3 cross 1 is 2. We have a simple way to find that there is no additional factor to obtain the value of the cross product of two Cartesian unit basis vectors. We introduce epsilon I, j, k, and here these three are I, j, and k are vector indices 1, 2, or 3. And in here, cross product vanishes if they are either parallel or anti-parallel. Therefore, these two must be different. So we have to choose two indices, first two indices, they are different. If it is not the case, this value equals 0. And next we consider k. This is k. K survives only if k is different from I and j. Because this one survives only if I is different from j. So as a result, all of the indices I, j, k, they must be different. That means because they are coming from 1, 2, and 3, so ijk survives. If epsilon ijk survives, only if ijk construct a permutation of 1, 2, 3. We define the epsilon 1, 2, 3 equals plus 1 because we know E1 cross E2 equals E3. Here, this 1 came from E1, this 2 came from E2, and this 3 came from this E3. And there is no sign. It is a positive sign, so it is a given. It's a value of the Lebesgue tensor for the elementary. The fundamental value is plus 1. If I exchange the order E2 cross E1, then its value is, we know, it is minus E3 because of the anti-commutative relation of the cross product. Therefore, if I exchange any two, especially I and j, then the sign flips. So while epsilon 1, 2, 3 equals a plus 1, epsilon 2, 1, 3 equals a minus 1. What happens if I exchange this 1 and 3 one more time? Then I would get epsilon 2, 3, 1. And the value of the epsilon 2, 3, 1 is E2 from the fact that E2 cross E3 equals a plus E1. We find that it is again plus 1. In this manner, we can find that all of the three positive values for the Lebesgue tensors is 1, 2, 3, 2, 3, 1, and 3, 1, 2. We call these three permutations 1, 2, 3, 2, 3, 1, and 3, 1, 2 to be three even permutations. The other three permutations are giving this Lebesgue tensor to be minus 1. And those are permutations are 3, 2, 1, 1, 3, 2, and 2, 1, 3. We recall that if I list all three numbers 1, 2, 3, and I can place all three of them once in here. If I choose a number, allocate the first position, then I have only two remaining numbers. And then if I fill the two blanks already, the last one is filled automatically. This is the multiplication called 3 factorial, and this is the number of distinguishable permutations. Among 6 permutations, I have 3 even permutations that give Leibniz-Civita tensor to be plus 1, and the remaining 3 are the permutations gives Leibniz-Civita tensor to be minus 1. Otherwise, every Leibniz-Civita tensor must be 0. To express this multiplication table, actually we have a 3 by 3 cases. Among them, it is always expressed as a linear combination of 3 unit vectors, and they are expressed in this manner. And eventually, if I substitute explicit values for ij, then I have only 6 non-vanishing elements in the multiplication table. Next, we consider a triangle whose 3 sides are represented by vectors small a, b, and c. For simplicity, we have chosen the direction of the 3 vectors so that their head and tails are connected in series to return to the original point after a single turn. Then the area of the triangle is just 1/2 of the area of the parallelogram spanned by any 2 sides. This is giving the law, the sine law, and sine law comes directly from the definition of cross product to represent the area of the triangle. And the area of the triangle is this, this, this. Okay, absolute value. By the way, the reason why we have chosen the direction of the 3 vectors is to unify the direction of the cross products. A cross B, B is here, A is here. We are rotating A to B, so its normal vector is coming out of the plane. In a similar manner, B cross C, B cross C, this angle, this cross product has also the same direction that is coming out of the plane, and C cross A again. Therefore, as well as the magnitudes are the same, explicit vector A cross B, B cross C, and C cross A are exactly the same. In addition, the unit vector that is coming out of the plane can be obtained by dividing A cross B by its own magnitude. Similar manner, B cross C divided by its magnitude, C cross A divided by its magnitude. If I exchange the order of the cross product, there should be negative sign on it. Therefore, because this is the area multiplied by the unit vector, actual area can be obtained by taking the scalar product of the unit vector and hat. As a result, area can be expressed in this manner. Sure, if I exchange the order, it is B cross A and negative sign, C cross B, negative sign, A cross C, and negative sign. Because these three side vectors are connected in series, the sum is always 0. We recall that the area of this triangle is, for example, A, B, and theta. This is 1/2 AB sine theta. And because this sine theta is a positive, it is a 1/2 AB square root 1 minus cosine square theta. And if I insert this AB into the square root, it is a 1/2 A squared B squared minus A squared B squared cosine square theta. This is nothing but A squared AB cosine theta squared. That is A dot B squared. Okay, therefore the area of the triangle is 1/2 square root A squared B squared minus A dot B squared. This is true for any cases AB, BC, and CA. Okay, so next okay, that's it. We have shown everything. Next we consider second law. This is actually the law of sine. And next we consider the second law of cosine. Because we have a very simple identity, I can move A, B, or C to the right hand side and square the equality. Then we have these three relations. If I expand this, I have, for example, the first one, A squared plus B squared plus 2A dot B equals C squared. Move this one to the right hand side, and we have AB, 2AB cosine theta, where theta is the angle between A and B, equals C squared minus A squared minus B squared. So we divide both sides by 2AB, 2. Then we have A dot B, this is A dot B, expressed in terms of the linear combinations of the squares. So this is the law of cosine. Perhaps in the middle school or high school, you must have seen the formula of the area of a triangle expressed in terms of the side lengths A, B, and C. This is called the Heron's formula, and we make use of a vector algebra to prove the Heron's formula. It is convenient to define a function named after the particle physicist Callan. So this is Callan function, a symmetric function, cyclic function. Okay, we remember this is A cross B's square. That is one is A squared B squared sine squared theta, and this is A squared B squared 1 minus cosine squared theta. And we recall the second law of cosine, this, and we substitute this one in here. A dot B is always expressed in this manner. So substitute. I factor this 1/4. This squared is 1/4 factored out, and we have this form. 4 is multiplied here because I factored this 1/4 out. If I expand this, we have fourth power, A to the fourth, B to the fourth, C to the fourth, ABBCCA products. By the way, we have, because of the negative sign, we have a single negative sign and the other two has a positive sign. However, because of this term, this one, sum of these two make everything the same is an over factor. We find this is identical to each other except that there is a minus 1/4. So this is we have proved this identity. Why don't we substitute this one into the formula of the area? That is the area. Okay. This is to prove, and our area formula is given in here. Okay, so this is S equals 1/2 square root A cross B squared, right? And this is A cross B squared. So we can substitute this one to find finally that the area of a triangle can be expressed in terms of Heron function, and that reproduces Heron's formula. So you in the middle school and high school, you trained a lot to expand and factorize. So I believe you can follow this calculation. But you'd like to also check it by using it's it's a fun. Let's see. First of all, I bring Mathematica. And this is our PDF file. Copy the program, Control C and Control V. Shift plus Enter. Okay, this is the definition of Heron function, and the lam2 is the factorized form that is displayed in the lecture note. And we substitute lam1, let's see, and Mathematica doesn't expand or simplify if I do not ask. So lam1 in here, and then full simplify the difference between lam1 a squared b squared c squared and the factorized form. Finally, if I subtract and full simplify this expression, it gives a 0. So our proof by hand is reproduced by computer. You also want to make use of reduce. So launch the reduce session and copy reduce program, Control C and Control V, enter. You find the subtraction gives a 0. You can find this is a Heron function. The style, the grammar of reduce is different from Mathematica, but logically the same. Operator lam1, lam2. This one means I claim lam1 and lam2 are function. For or something, I'm defining the function. Don't forget to add asterisk to represent the multiplication of symbols in reduce, while Mathematica doesn't, we do not have to put the asterisk to represent the multiplication. And then there is this one, factorize this complicated expression. If I ask it to factorize, it gives the list, and these are factors, and this number 1 is a power of that factor. So we have 4 linear factors. Okay, so today, using the vector algebra, we were able to reproduce Heron's formula in a very simple way, and the tedious calculation of factorization or expansion were reproduced by computer algebra in a very, very easy way. The most of the development of the vector algebra and vector calculation was developed by a physicist. Sure, at the time, physicists, mathematicians, they were the same people. Now, however, most of mathematicians do not know physics very well. And for example, in our school, freshman mathematics major freshman doesn't take a physics course, so eventually they are not very familiar with the physics problem. But in physics, we need to learn mathematical tools in view of the physics. So it is not a good idea to take a mathematics course to study the mathematical tools that is necessary in physics. We do not require that very abstract method they are concentrated on in mathematics class. It's enough to study mathematical tools, to study engineering or physics in physics class. So please remember. Okay, that's it for today. Thank you.